13 billion light-years out, the impossible stares back. Galaxies too bright to exist, black holes too massive for their age, crimson dots burning where nothing should shine. Every telescope image shatters what we thought we knew. Ready to see what is really out there? Hit subscribe. These are not glitches in the data, they are cracks in reality, windows into a universe where invisible matter powers visible stars, where darkness feeds light. One breath. Then we plunge into cosmic dawn. The James Webb Space Telescope floats 1 million miles from Earth, staring into darkness. Its mirror stretches 21 feet across, coated in gold thin as a human hair. But size alone does not explain what it sees. Webb looks at light that traveled for over 13 billion years. These photons left their galaxies when the universe was barely 3% of its current age. Back then, the cosmos was smaller, hotter, denser. The first stars had just begun to burn. Before Webb launched, we sent Hubble. That telescope pushed the boundaries for 3 decades. It found galaxies from when the universe was 500 million years old. Impressive, yet limited. Hubble could not see far enough into the infrared spectrum. It missed the most ancient light. Webb changes everything. Its instruments detect infrared wavelengths that Hubble cannot touch. When distant galaxies race away from us, their light stretches. Blue becomes red, visible becomes infrared. The faster they recede, the redder they appear. This redshift reveals their age. The earliest galaxies Webb observes have redshifts above 10. Some reach 15 or higher. These numbers sound abstract until you realize what they mean. A galaxy at redshift 13 existed roughly 300 million years after the Big Bang. We are witnessing cosmic dawn itself. Scientists designed Webb specifically for this hunt. They pointed it at tiny patches of sky and exposed the sensors for hours, sometimes days. The telescope gathered every scrap of ancient light. What emerged shocked everyone. Galaxies appeared where theory said they should barely exist. Not just a few dim smudges. Bright, structured systems filled the images. Their light carried signatures of heavy elements: carbon, oxygen, nitrogen. These atoms form inside stars, then scatter when those stars die. The presence of these elements means multiple generations of stars already lived and perished. How did so much happen so fast? The universe at 300 million years old should have been simpler. Mostly hydrogen and helium, with stars just beginning their first cycles. Yet Webb shows complexity that defies the timeline. Each observation pushes the record farther. First, a galaxy at redshift 11, then 12, then 13.2. Each discovery forces us to reconsider how quickly structure can form, how fast gravity can pull matter together, how rapidly stars can ignite and die and scatter their remains. The implications spread through every corner of cosmology. If galaxies assembled this quickly, our models of dark matter need revision. If stars formed this efficiently, our understanding of gas physics breaks down. If heavy elements appeared this early, stellar evolution happens faster than we thought. But the biggest mystery is still ahead, because what Webb sees is not just early, it is wrong. Astronomers call them blue monsters. The name fits. These galaxies burn with ferocious intensity, radiating energy that should not be possible for their age. Brightness in astronomy depends on mass. More stars mean more light. A typical galaxy contains hundreds of billions of stars. Their combined output determines how bright the galaxy appears from Earth. Simple physics. Or so we thought. Blue monsters throw this logic into chaos. They shine with the luminosity of mature galaxies, yet exist when the universe was less than 500 million years old. That gives them barely enough time to form a few generations of stars, certainly not enough to build the stellar populations their brightness suggests. One blue monster galaxy catalogued early in Webb's mission radiates as much light as the Milky Way. Yet it formed during cosmic dawn. Our galaxy took over 13 billion years to assemble its current mass. This object achieved comparable brightness in a fraction of that time. The color adds another puzzle. Most ancient galaxies appear red when viewed through Webb. Their light has stretched across the expanding universe for so long that even blue stars look crimson. But these monsters retain a blue tint in the data. That means they are producing massive young stars at incredible rates. Young, massive stars burn blue and hot. They consume fuel rapidly, dying in just a few million years. For a galaxy to stay blue, it must constantly make new ones. Blue monsters somehow maintain this frenzied star formation in an era when gas should be scarce and difficult to compress. Scientists measure star formation rates in solar masses per year. A quiet galaxy might form 1 or 2 masses annually. The Milky Way averages about 3. Blue monsters exceed 100. Some burst past 500. They are factories running at speeds that break every simulation. Simulations predicted that early galaxies would grow slowly. Dark matter halos would gradually accumulate gas. That gas would cool over millions of years, then condense into stars. The process should be gentle, incremental. Blue monsters ignore this script entirely. Their brightness also implies tremendous mass. Mass requires time to gather. Gravity pulls matter together. But that pull takes millions of years to concentrate enough material for a galaxy. Blue monsters compress this timeline to impossible brevity. They appear fully formed when they should barely be starting. Researchers ran the numbers repeatedly. They checked for errors in the observations. They considered alternative explanations. Perhaps the distance measurements were wrong. Perhaps the brightness calculations had mistakes. Every check confirmed the original findings. Blue monsters are real. They are bright, they are young, and they should not exist. The universe at cosmic dawn was supposed to be simple, pristine, slowly waking up. Instead, Webb reveals a cosmos already ablaze with activity, already building structures that our best theories cannot explain. Something powered these galaxies to brilliance far ahead of schedule. The question is what? Dust sounds trivial. It is not. In space, dust tells the story of death and birth. Stars die and scatter their remains. Those remains include carbon, silicon, oxygen. These atoms clump together into tiny grains. Dust. Every mature galaxy swims in dust. It blocks light from distant stars. It glows in infrared as it absorbs and re-radiates energy. Astronomers use dust to measure how many stars have lived and died. More dust means more stellar generations, more history. Blue monsters have almost none. Webb measures dust by analyzing how galaxies absorb and emit different wavelengths. Dust grains block certain colors of light while letting others through. They also heat up and glow at specific infrared wavelengths. These signatures act like fingerprints. When scientists examined blue monster spectra, they found the fingerprints missing. The galaxies emit light cleanly across the spectrum. No significant blocking, no infrared glow from warm dust. Just pure starlight pouring into space. This contradicts everything about stellar evolution. Stars create heavy elements through fusion. They forge carbon in their cores, silicon in their outer layers, iron in their final explosive moments. When they die, they release these elements. Over time, the elements form dust. Blue monsters shine as bright as galaxies filled with billions of dead stars, yet they lack the dust those deaths should produce. Either the stars never died, which physics forbids, or something removed the dust, which no known process can do efficiently enough. One hypothesis suggests the stars are so young that they have not had time to die yet. But that creates another problem. Young, massive stars burn through fuel in mere millions of years. Blue monsters existed hundreds of millions of years after the Big Bang. plenty of time for early stars to complete their cycles. Another idea proposes that powerful stellar winds blow dust away. Massive stars generate fierce radiation pressure. This pressure can push on dust grains, driving them out of the galaxy. However, simulations show this process works slowly. It cannot clear a galaxy in the time available. Perhaps the dust exists, but hides in configurations that Webb cannot easily detect. Maybe it clumps in dense pockets instead of spreading evenly. Maybe it sits in regions that do not emit the expected infrared signals. Researchers tested these scenarios. None fit the data well. The absence of dust also affects star formation. Dust helps gas clouds collapse. It radiates away heat, allowing clouds to cool and compress under their own gravity. Without dust, forming new stars becomes harder. Yet blue monsters form stars at outrageous rates. They manage to build enormous stellar populations without accumulating the debris those populations should create. They continue making new stars without the dust that should facilitate the process. Every explanation runs into contradictions. The observations point to a type of object that should not function according to known astrophysics. But there it is, burning bright, dust-free, impossible. Before Webb launched, scientists spent decades building simulations. They modeled how the first galaxies formed. They input the laws of physics. They included dark matter, gravity, gas dynamics. They ran the calculations on supercomputers for months. Not one simulation produced blue monsters. The models predicted that early galaxies would be faint. They would grow slowly as gas trickled into dark matter halos. Star formation would proceed at modest rates. The galaxies would be small, dim, and gradually brightening over billions of years. Instead, Webb found galaxies that blazed into existence like firecrackers, bright from the start, massive from the start, forming stars at rates that exceeded anything the simulations generated. Cosmologists design simulations by encoding fundamental physics. They include equations for gravity, thermodynamics, radiation pressure, and more. They simulate volumes of space containing millions of dark matter particles. They track how these particles interact and how gas responds. The simulations successfully reproduced many features of the modern universe. They matched the distribution of galaxies we see today. They predicted the sizes and shapes of galaxy clusters. They explained how cosmic structure grew from tiny fluctuations in the early universe, but they failed at cosmic dawn. The problem lies in the assumptions. Simulations assume that star formation follows rules derived from studying nearby galaxies. They assume that gas must cool slowly. They assume that feedback from stars regulates how fast new stars form. These assumptions work beautifully for the recent universe. At cosmic dawn, the rules may have been different. Gas at that time was almost pure hydrogen and helium, no heavy elements to help it radiate heat efficiently. This should make cooling harder, slowing star formation. Yet blue monsters formed stars faster than modern galaxies. Dark matter halos at cosmic dawn were smaller and less massive. Smaller halos provide weaker gravitational wells. Weaker gravity should mean slower gas accumulation, yet blue monsters assembled mass at breakneck speed. Radiation from the first stars should have heated surrounding gas, preventing it from collapsing further. This negative feedback should have limited star formation. Yet blue monsters ignored this limit entirely. Scientists revisited their code. They adjusted parameters. They tested different prescriptions for star formation efficiency. Some tweaks produced slightly brighter early galaxies. None came close to matching blue monsters. The gap between prediction and observation is not small, it is enormous. Blue monsters are 10 to 100 times brighter than the brightest galaxies the simulations produce. That is not a minor discrepancy. It is a fundamental breakdown. Some researchers proposed that the simulations missed key physics. Perhaps dark matter behaves differently than assumed. Perhaps gas cools through unknown mechanisms. Perhaps star formation operates under different laws at high redshift. Others suggested that the observations might be misinterpreted. Perhaps what appears as a single bright galaxy is actually multiple fainter ones close together. Perhaps gravitational lensing amplifies the light. Detailed analysis ruled out most of these alternatives. The conclusion is unavoidable. Something happened at cosmic dawn that our models do not include. Something powered galaxies to extraordinary brightness. Something that remains invisible in our equations. At the center of most galaxies sits a black hole, not the small kind formed from a single dying star. A monster, millions or billions of times heavier than our star, supermassive. These objects grow by swallowing matter. Gas spirals inward, heats up, and eventually crosses the event horizon. With each meal, the black hole gains mass. Over billions of years, a tiny seed can grow into a giant. That is how it is supposed to work. Slow accumulation across cosmic time. Webb found black holes that skipped this process. One galaxy called UHZ1 sits 13.2 billion light-years away. The light we see from it left when the universe was only 3% of its current age, about 400 million years after the Big Bang, barely enough time for the first stars to form. At the heart of UHZ1 burns a supermassive black hole. Observations suggest it weighs as much as tens of millions of suns, perhaps even hundreds of millions. The exact number is still debated, but even the low estimates pose a severe problem. Black holes grow by eating. They pull in gas and stars from their surroundings, but there is a limit to how fast they can feed. When matter falls toward a black hole, it heats up and emits radiation. That radiation pushes back on incoming material. This effect, called the Eddington limit, caps the growth rate. Even if a black hole feeds continuously at the maximum rate, growing from a stellar remnant to supermassive size takes hundreds of millions of years at minimum. UHC-1 existed when the universe was only 400 million years old. That leaves almost no time for growth. The seed must have been huge to start with. Regular stars that collapse into black holes produce seeds weighing perhaps 10 to 100 solar masses. Starting from such a seed and growing at the Eddington limit gets you nowhere near the mass observed in UHZ1. The math does not work. Scientists proposed intermediate mass black hole seeds. Maybe the first black holes started heavier, forming from the collapse of massive primordial stars. Stars weighing hundreds or even thousands of solar masses. These could produce black hole seeds weighing up to a few thousand solar masses. Better, but still insufficient. Growing from a few thousand to a few hundred million in just a few 100 million years requires feeding rates that exceed the Eddington limit, continuously, without interruption. Nature rarely cooperates with continuous processes. Gas supplies fluctuate. Stellar winds disrupt feeding. Mergers with other galaxies temporarily halt accretion. Any of these interruptions would make the timeline even tighter. UHZ1 is not alone. Webb has identified multiple galaxies at similar distances with similarly massive black holes. Each one presents the same impossible timeline. Each one demands an explanation that standard astrophysics cannot provide. The black holes are there. They are massive. They are young. We need to find out how. The question haunts astronomers. How do you build a giant in the blink of an eye? Standard growth requires time and patience. A black hole accretes gas from its surroundings. The gas forms a swirling disk around the black hole. Friction heats the disk to millions of degrees. The hot gas radiates intensely, producing the bright quasars we observe across the universe. This radiation serves as a brake. It pushes back on incoming gas. The stronger the radiation, the harder it becomes for more matter to fall in. This is the Eddington limit. A black hole can only grow so fast before its own light strangles its food supply. Calculations show that a black hole feeding at the Eddington limit doubles its mass every few tens of millions of years. Starting from a seed weighing 100 solar masses, you need about 500 million years to reach 1 billion solar masses. The universe at UHZ1's era was only 400 million years old. The numbers do not add up. Some researchers suggest super Eddington accretion. Maybe early black holes found ways to exceed the limit. Perhaps the gas was extremely dense, overwhelming radiation pressure. Perhaps magnetic fields channeled matter inward despite the photon push. Simulations show this might work in specific conditions. But super Eddington feeding is unstable. It tends to blow itself apart. The black hole ejects huge amounts of gas in powerful winds. These outflows reduce the net mass gain. Even optimistic models struggle to achieve the necessary growth rates. Another approach focuses on the seeds. If you start with a heavier seed, you need less growth. A 10,000 solar mass seed requires only about 10 doublings to reach 10 million. A 100,000 solar mass seed needs even fewer. The challenge becomes explaining where such heavy seeds come from. Massive primordial stars could provide heavy seeds. In the early universe, gas was almost pure hydrogen and helium. Without heavier elements to radiate heat efficiently, gas clouds could grow very large before collapsing. Stars weighing thousands of solar masses might have formed. When they died, they would leave behind massive black holes. This helps, but it introduces new problems. Massive stars burn incredibly hot. Their intense radiation might blow away surrounding gas before a black hole can form. Even if a black hole does form, it might not immediately start feeding. It needs a supply of gas nearby, and the star's death might have cleared the area. Another idea involves direct collapse. Instead of forming a star first, a gas cloud might collapse straight into a black hole. This requires special conditions. The gas must avoid fragmenting into smaller clumps. It must stay hot enough to resist normal star formation, but cool enough to collapse under gravity. Simulations suggest this can happen in rare environments. Perhaps 1 in a million dark matter halos experiences the right conditions. If so, direct collapse could produce seeds weighing tens of thousands of solar masses. From there, reaching supermassive status becomes plausible. Yet even this struggles to explain the sheer number of massive black holes Webb observes. They appear too common for such a rare process. Among Webb's strangest discoveries are the little red dots, tiny points of crimson light scattered across deep images. They look insignificant at first, small, faint, easy to overlook. But their properties defy explanation. These objects are compact, really compact. They emit light from regions smaller than our solar system, yet they shine with the luminosity of entire galaxies. Cramming that much energy into such a small volume requires something extreme. Their color gives them their name. They appear red in Webb's images, not the stretched red of distant galaxies receding through cosmic expansion, a different red. The spectrum shows strong emission at specific wavelengths. These wavelengths correspond to ionized gas heated to extreme temperatures. Little red dots sit at high redshifts. They date back to cosmic dawn, contemporary with blue monsters and early massive black holes. They existed when the universe was less than 1 billion years old, another piece of the cosmic dawn puzzle. What makes them truly bizarre is what they do not emit: X-rays. Almost every known compact energetic object produces X-rays. Accreting black holes blast X-rays as gas heats to millions of degrees before falling in. Neutron stars emit X-rays from their scorching surfaces. Even active star-forming regions generate X-rays from hot stellar winds. Little red dots produce virtually none. Researchers pointed X-ray telescopes at their locations. Nothing. The limits are so stringent that normal explanations collapse. If these are accreting black holes, they would need to be feeding in ways never observed elsewhere. If they are dense star clusters, they would need to avoid creating the hot gas that generates X-rays. The lack of X-rays also rules out typical quasars. Quasars are among the brightest objects in the universe, powered by supermassive black holes consuming vast amounts of gas. They radiate across the entire electromagnetic spectrum, including powerful X-ray emission. Little red dots do not fit this profile. Perhaps they are heavily obscured. Maybe thick clouds of gas and dust surround them, blocking X-rays but letting through visible and infrared light. This works for some objects, but little red dots show no evidence of large dust columns. The obscuration would need to be perfect, selective, and unlike anything else observed. Another idea suggests they might be transitional objects. Perhaps they represent a phase between one type of cosmic entity and another, a stage that lasts only briefly before evolving into something more familiar. If so, we are witnessing them during a narrow window of time. Some spectra from little red dots show unusual features: broad emission lines indicating rapid gas motion, narrow absorption features hinting at cooler material in the foreground. The combination does not match standard models of galaxies, quasars, or stellar populations. Each new observation deepens the mystery. Little red dots refuse to fit into established categories. They occupy a strange space between known phenomena: bright but compact, energetic but X-ray quiet, ancient but unlike anything from that era predicted by theory. They exist. Webb sees them. We just do not know what they are. Before stars, before galaxies, before light, there was dark matter. It filled the universe, invisible and silent. It does not emit light. It does not absorb light. It barely interacts with anything except through gravity. But gravity is enough. Dark matter clumped together in the early universe. Small variations in its density grew over time. Regions slightly denser than average pulled in more matter. Those regions became denser still, pulling in even more. This process repeated, amplifying tiny fluctuations into significant structures. By a few 100 million years after the Big Bang, dark matter had organized itself into halos, not the massive halos that host galaxies today, tiny ones, microhalos, each one weighing roughly as much as a few thousand to a few million suns, barely noticeable on cosmic scales. These microhalos acted as gravitational wells. They sat there, pulling on everything around them. At first, they contained only dark matter, but the universe also held gas, hydrogen and helium left over from the Big Bang. That gas began to feel the pull. Slowly, gas drifted into the microhalos. Gravity drew it inward. The gas did not fall in all at once. It settled into orbits, swirling around the dark matter. Over time, collisions between gas particles removed energy. The gas lost speed and spiraled deeper into the halo. This process took millions of years. The microhalos provided stable anchors while the gas cooled and concentrated. Without dark matter, the gas would have been too diffuse to collapse on its own. It needed the extra gravity that dark matter provided. Eventually, the gas density at the centers of microhalos became high enough for something new to happen. Atoms collided more frequently. Temperatures dropped as the gas radiated away energy. Pressure decreased. When pressure drops below a critical threshold, gravity wins. The gas collapses. This collapse marked the birth of the first stars, the cosmic dawn. But not all microhalos behaved identically. Some had higher dark matter densities, some had more gas. Some sat in regions where surrounding radiation from other stars heated the gas, preventing collapse. Only specific microhalos provided the right conditions for star formation. Those special microhalos became the nurseries of the universe. They turned invisible dark matter scaffolding into visible stellar light. They transformed the cosmos from a dark expanse into a place studded with glowing points. Dark matter also played another crucial role. It determined where stars formed. Gas could only collapse in regions where dark matter had already gathered. This meant the first stars appeared in specific locations, not randomly scattered, concentrated in the densest parts of the early cosmic web. The distribution of dark matter microhalos shaped the entire structure of the early universe. It set the stage for everything that followed: galaxies, clusters, superclusters. All of it traces back to those tiny, invisible halos that formed before the first photon of starlight ever shone. We cannot see the dark matter directly, but we see its effects, the patterns it created, the structures it enabled. And according to new research, dark matter may have done more than just provide scaffolding. It may have powered the stars themselves. Picture the early universe. No stars yet, no galaxies, just gas. Hydrogen and helium stretching across space. Thin, almost nothing, but not quite. This gas was the raw material for everything. Every star, every planet, every atom in your body. It all started as primordial hydrogen and helium, but gas alone does not make stars. It needs to collapse. Collapse requires gravity. Gravity pulls matter together, but it fights against pressure. Pressure pushes outward. Hot gas has high pressure. As long as the pressure balances gravity, nothing collapses. The gas just sits there. Cooling breaks the balance. When gas radiates energy, it cools. Cooler gas has lower pressure. Lower pressure means gravity starts winning. The gas begins to contract. As it contracts, it grows denser. Denser gas radiates more efficiently. It cools faster. The collapse accelerates. In the modern universe, gas cools using heavy elements: carbon, oxygen, nitrogen. These atoms radiate energy efficiently at relatively low temperatures. They help gas clouds cool down to just a few tens of degrees above absolute zero, perfect for making stars. Primordial gas had none of these elements, just hydrogen and helium. These atoms radiate poorly at low temperatures. The gas could not cool below a few thousand degrees. That sounds cold, but it is actually quite hot compared to modern star-forming regions. Hot gas has higher pressure. Higher pressure resists collapse. This means primordial gas clouds needed more mass to overcome the pressure. They had to be heavier, more massive. The first stars likely weighed hundreds of times more than our closest stellar neighbor. Massive stars burn fiercely. They consume their fuel in just a few million years. Then they explode. The explosion scatters the heavy elements created inside the star. These elements mix with the surrounding gas. Now the gas can cool more efficiently. The next generation of stars can be smaller. But before that first generation died, the universe was stuck with massive stars. Hot, bright, short-lived. These stars pumped enormous amounts of energy into their surroundings. Their ultraviolet light ionized nearby gas. Ionized gas has even higher pressure. This made further collapse harder. The process created a competition. Gravity tried to pull gas into dark matter halos. Radiation from existing stars tried to heat that gas and blow it away. In most regions, radiation won. Star formation shut down. Only the densest halos, with the deepest gravitational wells, could continue accumulating gas. This explains why early galaxies should have been faint. Limited gas supply, difficult cooling, strong feedback from existing stars. Everything conspired to keep star formation rates low. Yet blue monsters exist. They formed stars at enormous rates. Somehow, they overcame all these barriers. They accumulated gas despite radiation pressure. They cooled gas despite lacking heavy elements. They built stellar populations that should have taken billions of years to assemble. Standard gas dynamics cannot explain it. Normal star formation physics falls short. The clouds that fed blue monsters must have behaved differently. Perhaps they had help. Perhaps something else participated in the collapse. Something beyond just hydrogen and helium. Something dark. Dark matter particles might destroy each other. Annihilation. When a dark matter particle meets its antiparticle, they can collide and vanish. Their mass converts into energy, pure energy flooding into the surrounding space. Normally, dark matter is too sparse for this to matter. The particles rarely encounter each other. Annihilation happens, but so infrequently that the energy release is negligible. You would never notice it. But inside the dense cores of microhalos, the situation changes. Dark matter particles pack tightly together. They pass close to each other constantly. The annihilation rate skyrockets. Suddenly, the energy output becomes significant. Now, imagine a cloud of hydrogen and helium collapsing inside such a halo. As the cloud contracts, it sinks deeper into the dark matter concentration. The dark matter density increases. Annihilation accelerates. Energy pours into the gas. This energy heats the gas. But unlike the heat from nuclear fusion, which comes later, this heat spreads throughout the entire cloud. It does not require the extreme temperatures and pressures at a star's core. It just needs dark matter particles to meet and annihilate. The heating from dark matter annihilation can stabilize a collapsing cloud. The cloud contracts under gravity. Dark matter annihilation heats it. Gravity pulls harder. Annihilation heats more. The two forces balance. The cloud stops collapsing before it reaches the densities needed for fusion. You get a star without fusion, a dark star. These objects would look strange, much larger than normal stars, cooler on the surface, because the heat comes from dark matter annihilation spread throughout the volume rather than a tiny fusion core. But they can still shine brightly. The total energy output depends on how much dark matter annihilates. In halos with extremely high dark matter densities, the annihilation rate could be enormous. A single dark star might emit as much energy as millions of normal stars. It would blaze with impossible brightness, not from fusion, from the invisible matter that fills it. Dark stars could also grow massive. Normal stars face a limit. Above a few hundred solar masses, radiation pressure becomes so intense that it blows the star apart. The star cannot hold itself together. Dark stars bypass this limit. The energy from dark matter annihilation distributes more evenly. It does not create the same intense radiation pressure at the surface. The star can accumulate far more mass. Theoretical models suggest dark stars might grow to tens of thousands or even millions of solar masses, giants that dwarf anything fusion-powered. They would be cool, extended, and unimaginably bright. Eventually, the dark matter fuel runs out. The halo cannot sustain the annihilation rate forever. When that happens, the dark star loses its energy source. Gravity takes over. The star begins collapsing again. Now it finally reaches the densities needed for fusion. Or it might skip fusion entirely. If the star is massive enough, it collapses straight into a black hole, a supermassive seed, born from the death of a dark star. This could solve everything. Blue monsters, massive black holes, little red dots, all of them powered or seeded by dark stars. Size matters in astronomy. A star's mass determines everything about it: how hot it burns, how long it lives, how bright it shines. Normal stars follow strict rules. Dark stars break them. Regular stars have an upper limit. Above roughly 250 solar masses, they become unstable. The radiation pressure from their cores pushes outward with such force that it overcomes gravity. The star tears itself apart before it can grow larger. This limit has held across every observation we have made. Dark stars ignore this boundary. The difference lies in how they generate energy. Normal stars fuse hydrogen in their cores. The fusion happens in a tiny region at the center where temperatures reach millions of degrees. This concentrated energy source creates intense radiation pressure that pushes outward from the core. Dark stars spread their energy production throughout their entire volume. Dark matter particles annihilate wherever they meet. In the dense center, annihilation happens frequently. In the outer layers, less so. But it still happens everywhere. The energy does not concentrate in one spot. This distributed heating changes the game. The star does not develop the same crushing radiation pressure at its core. It can support much more mass. Gravity can pull in more material without the star fighting back as violently. Theoretical calculations suggest dark stars could reach 10,000 solar masses. Some models push to 100,000. A few extreme scenarios allow for 1,000,000. These numbers sound absurd. They are larger than entire star clusters in modern galaxies. But the early universe provided ideal conditions. Dark matter densities were higher. Microhalos concentrated dark matter into small volumes. Gas had nowhere else to go. It fell into these halos and accumulated. Dark stars formed in the sweetest gravitational wells, where both dark matter and gas reached maximum density. As a dark star grows, it captures more dark matter. More dark matter means more annihilation. More annihilation means more energy to support even greater mass. The process feeds on itself. The star can balloon to gigantic proportions. A dark star weighing 100,000 solar masses would dwarf anything in our night sky. If you could see one from Earth, it would appear as bright as a small galaxy, but it would be a single object, one enormous ball of gas held together by gravity and heated by invisible particles destroying each other inside. These giants would not last forever. Dark matter in the halo is finite. As the star consumes it through annihilation, the supply dwindles. Eventually, the annihilation rate drops. The energy output decreases. The star can no longer support its tremendous mass. When that happens, gravity takes control. The star begins to collapse. What comes next depends on the mass. Smaller dark stars might ignite fusion and become incredibly luminous fusion-powered supergiants. Larger ones skip fusion entirely and go straight to black hole formation. Either way, dark stars represent a phase, a temporary stage in cosmic evolution. They shine brilliantly for a cosmologically brief period, then transform into something else. But during their time, they could light up the early universe like nothing else. Dark matter does not distribute evenly. It clumps. Some regions have more than others. This unevenness determines where stars can form and how bright they become. In areas with low dark matter density, microhalos are weak. Their gravity barely pulls on gas. What little gas they attract takes millions of years to settle. Star formation stutters or fails entirely. In high-density regions, everything accelerates. Strong gravity pulls gas inward rapidly. The gas concentrates quickly. Dark matter particles crowd together, annihilating at higher rates. The conditions for dark star formation become ideal. This creates a natural sorting mechanism. The universe at cosmic dawn had varying dark matter densities. Places where density peaked became hotbeds of activity. Places where it sagged remained quiet. Simulations show that density varies on all scales. Large regions might be overdense or underdense. Within those regions, smaller pockets show further variation. Within those pockets, microhalos concentrate dark matter even more. The densest microhalos became the sites of the first dark stars. These locations had everything needed: abundant dark matter for annihilation, deep gravitational wells for gas accumulation, minimal interference from external radiation. Once a dark star ignites in a high-density halo, it influences its surroundings. Its radiation ionizes nearby gas. This pressure prevents smaller halos from forming their own stars. The dark star monopolizes star formation in its neighborhood. When the dark star eventually dies, it has stirred the gas through stellar winds. It creates a legacy that affects subsequent star formation. Observations from Webb hint at this clustering. Blue monster galaxies do not scatter randomly. They appear in specific regions. regions that likely corresponded to high dark matter density zones in the early universe. The correlation between dark matter density and star formation intensity could explain blue monsters entirely. If dark stars form preferentially in the densest halos, they would produce exactly the brightness we observe. A single supermassive dark star in a dense halo could outshine millions of normal stars. A few in close proximity would create a blue monster, bright, compact, dust-free. Exactly what Webb sees. The dark matter density also affects how long dark stars can burn. Higher density means more particles available for annihilation. More fuel, the star sustains itself longer before exhausting its supply. In the densest environments, dark stars might shine for tens of millions of years, long enough to be observed in significant numbers across cosmic dawn, short enough that they vanished by later epochs, leaving no trace in the modern universe. This explains why we never see dark stars today. The conditions that created them no longer exist. Dark matter has spread out, densities have dropped. Modern star formation relies entirely on fusion. Dark matter still clumps into galaxy halos, but not densely enough to power stars through annihilation. The connection is clear. Dark matter density drove the nature of the first stars. Where density peaked, dark stars blazed. Blue monsters shine impossibly bright for their age. Dark stars offer the solution. Consider the numbers. A typical blue monster radiates with the power of hundreds of billions of normal stars, yet it formed when there was barely time to make a few million stars. The math fails unless something extraordinary happened. Enter dark stars. A single dark star weighing 100,000 solar masses produces as much light as 10 million ordinary stars. 10 such dark stars equal 100 million stars worth of brightness. 100 dark stars match a billion. You do not need hundreds of billions of individual fusion-powered stars. You need a handful of dark giants. This solves the timeline problem instantly. Normal stars require time to form, mature, and die before the next generation begins. Building a population of hundreds of billions takes billions of years. Building 100 dark stars in dense microhalos takes mere millions of years. The gas dynamics support this. In high dark matter density regions, gas flows into halos quickly. Multiple massive clouds can collapse simultaneously in a cluster of nearby microhalos. Each cloud forms a dark star. Within a few million years, you have a collection of these monsters. Their combined light output matches blue monster observations. Their spectrum would show the blue tint from hot surfaces. Their compact distribution explains why blue monsters appear small on the sky. Everything fits. The dust problem also disappears. Dark stars produce minimal heavy elements. They do not undergo the full fusion cycles that create carbon, silicon, and iron. Most of their energy comes from dark matter annihilation. When they die, they leave behind black holes rather than scattering enriched material. Without heavy element production, there is no dust. The galaxy remains pristine. Gas streams in, forms dark stars, those stars shine, then they collapse into black holes. Clean, efficient, dust-free. Star formation rates also make sense. Blue monsters form stars at hundreds of solar masses per year. If each dark star weighs tens of thousands of solar masses and forms in a few 100,000 years, the average formation rate works out perfectly. Exactly what observations show. The radiation signature clinches it. Blue monsters emit light with a spectrum that matches theoretical predictions for supermassive dark stars. Cool surface temperatures produce specific spectral features. These features appear in Webb data from blue monsters. One concern remains. Can dark stars really form in the numbers needed? Do enough high-density microhalos exist to create the population of blue monsters Webb observes? Simulations suggest yes. The early universe had plenty of dark matter structure. Millions of microhalos existed within the volume's Webb surveys. If even a small fraction had sufficient density to form dark stars, the numbers work. Not every dark star needs to be enormous. A mix of sizes creates the range of blue monster brightnesses Webb sees. Some appear extremely luminous. Others are dimmer, but still far brighter than expected. A population of varied dark stars explains the full distribution. Blue monsters are not impossible. They are dark star nurseries, galaxies where invisible matter powered visible light, where giants formed and shone before collapsing into the black holes that would eventually power quasars. Every supermassive black hole needs a beginning, a seed. Standard theory suggests these seeds come from the first normal stars, stars weighing perhaps 100 solar masses. When they die, they leave behind black holes weighing similar amounts. From there, the black hole accretes gas over billions of years, slowly growing, gradually reaching the millions or billions of solar masses we observe today. A long journey, too long for the black holes Webb finds. Dark stars offer a shortcut. When a dark star exhausts its dark matter fuel, it collapses. The collapse depends on the star's mass. A dark star weighing 10,000 solar masses collapses into a black hole weighing roughly the same. No billions of years needed. The seed starts massive. This changes the growth timeline completely. Starting from 10,000 solar masses instead of 100 means you need far fewer doublings to reach supermassive status. The Eddington limit still applies, but you reach the finish line much faster. A black hole seed, weighing 10,000 solar masses, can grow to 100 million solar masses in about 200 million years if it feeds continuously. The universe at 400 million years old provides ample time. The impossible timeline becomes possible, but dark stars can do even better. The most massive dark stars might weigh 100,000 solar masses or more. When they collapse, they create black hole seeds, already approaching intermediate mass. From there, reaching supermassive size requires only a few doublings. The collapse itself happens catastrophically fast. Once dark matter annihilation stops supporting the star, nothing prevents the implosion. The star has no fusion core to provide pressure. Gravity pulls everything inward at near free-fall speeds. Within hours or days, the dark star transforms into a black hole. The event horizon forms. The seed is born. Immediately, the black hole begins feeding on surrounding gas. Dark stars form in dense environments rich with material. When the star collapses, all that gas remains nearby. The new black hole has an immediate food supply. Unlike normal stellar collapse, which often blows away material in a supernova, dark star collapse might be quieter, less violent. More of the nearby gas remains available. The black hole starts growing right away. This rapid transition from dark star to accreting black hole accelerates supermassive black hole formation. Within a few 100 million years, you go from primordial gas to a fully formed supermassive black hole weighing hundreds of millions of solar masses. The numbers finally work. UHZ-1 and similar galaxies no longer pose an impossible puzzle. Their black holes grew from dark star seeds, seeds massive enough to reach supermassive status within the available time. This also explains why such black holes appear multiple times in Webb data. Dark stars were not rare flukes. They formed commonly wherever dark matter densities peaked. Each one became a black hole seed. Many of those seeds grew into the supermassive black holes that power quasars. The pathway is clear. Dark matter microhalo, gas collapse, dark star formation, growth to enormous mass, fuel exhaustion, catastrophic collapse, black hole seed, rapid accretion, supermassive black hole. One process explaining everything. Time is the enemy when building supermassive black holes. You need mass, lots of it, fast. Dark stars provide the express lane. The process begins with collapse. A dark star runs out of dark matter to annihilate. The energy supporting it vanishes. Gravity crushes the star inward. Within a day, a structure that spanned light years compresses into a point. A black hole forms, but this is just the start. The black hole sits in the same dense environment where the dark star formed. Gas clouds surround it. Dark matter halos channel more gas inward. Everything the dark star did not consume remains available. The black hole begins eating immediately. Normal black hole growth faces delays. After a star goes supernova, the explosion scatters gas. The black hole must wait millions of years for material to settle back. The feeding starts slowly. Dark star collapse avoids this. The gas stays put. Accretion begins at once. The feeding rate determines growth speed. Black holes pull gas into accretion disks. The gas spirals inward, heating through friction. Eventually, it crosses the event horizon. The black hole gains mass. Radiation from the hot disk creates pressure. This radiation pushes back on incoming gas. The Eddington limit describes the balance between inward gravity and outward radiation pressure. Feed too fast, and radiation blows away the food supply. Black holes from dark star collapse start with a major advantage. They are already massive. A 10,000 solar mass black hole has stronger gravity than a 100 solar mass black hole. Stronger gravity can overcome higher radiation pressure. The Eddington limit still exists, but the maximum feeding rate is much higher. A massive seed can double its mass in 20 million years. Do this 15 times, and you reach over 300 million solar masses. Total time, 300 million years. Perfectly reasonable for the cosmic dawn era. But it gets better. Some environments allow super Eddington accretion. If gas is extremely dense and cold, it can overwhelm radiation pressure. The black hole feeds faster than the Eddington limit predicts. Growth accelerates beyond the standard timeline. Dense microhalos at cosmic dawn might provide exactly these conditions. Gas streams in from all directions. It is cold, having cooled to form the dark star initially. The black hole sits at the center of a gravitational well that funnels material inward. Super Eddington feeding becomes possible. Even brief episodes of super Eddington accretion make a huge difference. If a black hole feeds at twice the Eddington limit for 50 million years, it gains as much mass as it would from 100 million years of normal feeding. You cut the required time in half. Combine massive seeds with occasional super Eddington feeding, and supermassive black holes assemble rapidly. Start with a 100,000 solar mass seed from a collapsed dark star. Feed at the Eddington limit for 100 million years. Enjoy a few super Eddington bursts. You reach several hundred million solar masses by 400 million years after the Big Bang. UHZ1 suddenly makes sense. Its black hole is not impossible. It is the natural result of dark star collapse followed by aggressive feeding in a dense early universe environment. The pathway is fast. Dark star collapse provides the massive seed. Dense environments provide the gas. Gravity provides the mechanism. Time provides just enough duration. The black holes Webb observes are not anomalies. They are the expected outcome when dark stars seed black hole growth at cosmic dawn. UHZ1 sits 13.2 billion light-years away. Its light left when the universe was 3% of its current age, only 400 million years after the Big Bang. An infant cosmos. Yet at its heart burns a supermassive black hole. The discovery came from combining Webb observations with X-ray data. Webb saw the galaxy. X-ray telescopes detected intense radiation from the center. The signatures matched an actively feeding black hole. A massive one. Estimates place its mass between 40 million and 140 million solar masses. Even conservative estimates create a timeline problem. Normal black hole growth cannot build something that massive that quickly. The galaxy itself appears unusual, very bright for its distance. Compact. The light comes from a region less than 1,000 light-years across. The Milky Way spans 100,000 light-years. UHZ-1 packs immense luminosity into a tiny volume. This compactness hints at extreme star formation or an incredibly active black hole, probably both. The galaxy furiously makes stars while its central black hole gorges on gas. Standard models struggle to explain UHZ-1. You cannot build the observed black hole from normal stellar remnants in time. You cannot form the stellar population through conventional star formation. Every path hits a wall. Dark stars demolish the wall. Imagine UHZ-1's region at cosmic dawn. High dark matter density. Gas streaming into dense microhalos. Multiple dark stars form. They grow massive. They shine brilliantly. Together, they create the extreme brightness Webb observes. Over tens of millions of years, these dark stars exhaust their fuel. One by one, they collapse. Each forms a black hole seed weighing tens of thousands of solar masses. Some merge, creating even larger seeds. One seed dominates. It sits at the deepest gravitational point. It captures the most gas. It grows fastest. Within 200 million years, it reaches tens of millions of solar masses. By 400 million years, it weighs what we observe today. The other seeds also grow. They orbit the central dominant black hole. Some merge with it. Others remain as satellites, feeding on whatever gas they capture. The result is UHZ-1 as we see it. A compact galaxy powered by dark star remnants. A central supermassive black hole fed by dark star collapse. All formed through the dark star pathway. This scenario fits every observation. The compactness comes from dark stars forming in a tight cluster. The brightness comes from multiple dark stars shining simultaneously. The black hole comes from dark star collapse into a massive seed that grows rapidly. UHZ-1 is not unique. Webb has found similar galaxies. Each likely followed the same path. Dark star formation, collapse into black hole seeds, rapid growth through accretion. These galaxies are windows into the dark star era. They show us what happens when invisible matter powers visible light. When giants form and die in the universe's infancy. UHZ-1 stopped being impossible the moment dark stars entered the picture. Now it is evidence. Proof that our understanding needs revision. Proof that dark matter played a more active role than we thought. X-rays reveal heat. When gas falls toward a black hole, friction heats it to millions of degrees. At those temperatures, atoms move incredibly fast. Collisions strip electrons. The hot plasma radiates X-rays. Every accreting black hole we have studied emits X-rays. From stellar mass black holes to supermassive ones, powering quasars. X-rays are the calling card of accretion. If you see a compact object radiating intensely and it produces X-rays, it is almost certainly a black hole feeding on gas. Little red dots break this rule. They shine brightly. They are compact. They show signs of extreme energy processes. But X-ray telescopes detect almost nothing. If these are black holes, where are the X-rays? One possibility is heavy obscuration. Maybe thick clouds surround little red dots, blocking X-rays while allowing visible and infrared light to escape. This works for some objects where enormous columns of material absorb X-rays completely. But little red dots show no evidence of such obscuration. Their spectra lack the signatures of dense absorbing material. The obscuration would need to block X-rays perfectly while being invisible in other wavelengths. Unlikely. Dark stars offer a different explanation. If little red dots are dark stars rather than black holes, they would not produce X-rays. Dark star energy comes from dark matter annihilation, not hot accretion disks. The annihilation heats gas, but not to the millions of degrees needed for X-ray emission. The gas stays hot enough to ionize, but cool enough to avoid X-rays. The spectrum fits this picture. Little red dots show strong emission lines from ionized hydrogen and other elements. The ionization levels indicate temperatures of tens of thousands of degrees. Hot, but not X-ray hot, exactly what dark stars would produce. Their compactness also matches dark stars. A dark star weighing 100,000 solar masses might span a few light years. From 13 billion light years away, this appears as a tiny point. Compact, bright, not from an accretion disk, from the star itself. The red color arises from Doppler shifting. Little red dots sit at high redshift. Their light has stretched during its journey. A hot blue dark star would appear red by the time its light reaches us. The observed color is an artifact of distance, not intrinsic temperature. Some little red dots show variability. Their brightness changes over months or years. Dark stars can vary if their dark matter annihilation rate fluctuates. Changes in the density distribution within the star could alter energy output. The lack of X-rays is not a mystery. If little red dots are dark stars, it is a prediction. Dark stars should not emit X-rays. They operate at lower temperatures. Their energy source does not create million-degree plasma. Webb sees little red dots because they existed at cosmic dawn when dark stars flourished. X-ray telescopes see nothing because dark stars do not make X-rays. The observations align perfectly. Little red dots might be our clearest view yet of dark stars in action. Not collapsed remnants, not black holes, the stars themselves shining with the power of annihilating dark matter. Spectroscopy reveals secrets. When light passes through gas, atoms absorb specific wavelengths. Each element absorbs at characteristic energies. The pattern tells you what elements exist and at what temperature. Webb carries spectrographs that split light into components. Scientists pointed these instruments at candidate dark stars, objects that appeared unusually bright and compact. The spectra showed something unexpected. Helium absorption features, strong ones. Helium is the second most abundant element. It formed during the Big Bang. Every star contains helium. But normal stars show helium absorption only under specific conditions. The star must have a particular surface temperature. Too hot, and helium ionizes completely. Too cool, and it does not absorb efficiently. Dark stars operate in a different temperature regime. Their surfaces are cooler than normal massive stars because their energy spreads throughout their volume rather than concentrating in a fusion core. This puts their surface temperature right where helium absorption becomes prominent. Theoretical models of dark stars predicted strong helium features. The models calculated what a dark star spectrum should look like. They included dark matter heating effects. They accounted for the extended atmosphere. They predicted specific absorption lines. When observers analyzed spectra from JWST 130, they found helium absorption matching predictions. The wavelengths aligned, the strengths matched, closer than any normal stellar model could explain. Another candidate, JWST 140, showed similar features. Again, helium absorption at expected wavelengths. Again, strengths consistent with dark star models. The pattern repeated. These are not definitive detections. Helium absorption can occur in other contexts. Some normal stars show helium features. Certain quasars produce helium lines. The observation alone does not prove dark stars exist, but it is consistent, and consistency matters. If these objects were normal stars, their helium features should differ. If they were typical quasars, other spectral signatures should appear. None of these alternatives fit as well as dark stars. The helium absorption also appears at the right redshift. The lines are shifted to longer wavelengths by exactly the amount expected for objects at cosmic dawn. This confirms the objects are genuinely distant and ancient. Some spectra show additional features. Carbon and oxygen lines appear weakly. This suggests the dark stars might have small amounts of heavy elements in their atmospheres. Perhaps they formed from gas that already contained trace metals from earlier stars. Or perhaps the dark stars themselves produced small amounts through limited fusion. The presence of metals complicates the picture slightly. Pure dark stars should form from pristine hydrogen and helium, but the early universe was messy. Gas from different sources mixed. Some clouds had metals, others did not. Dark stars forming from slightly enriched gas would show weak metal lines, while still being powered primarily by dark matter annihilation. The helium features remain the strongest signal. Multiple objects, consistent wavelengths, strengths matching theoretical predictions. Each detection adds confidence. Spectroscopy moves the dark star hypothesis from pure theory toward observational support. The predicted features appear. The puzzle pieces fit. JADE stands for JWST Advanced Deep Extragalactic Survey, one of the largest programs using Webb to study the early universe. It targets deep fields, tiny patches of sky observed for hundreds of hours. Among thousands of objects JADE's detected, a few stood out, too bright, too compact. Their spectra did not match normal galaxies or quasars. JADESGS 130 appeared first, a small red point in deep images. Initial photometry suggested high redshift. Follow-up spectroscopy confirmed it. The object existed when the universe was less than 400 million years old. The spectrum showed broad emission lines. Hydrogen glowed intensely. Helium absorption appeared strongly. The combination was unusual for objects at this distance. Researchers compared the spectrum to theoretical models. Normal stellar populations did not fit. The helium features were too strong. Quasar models failed as well. The emission line ratios were wrong. Then they tested dark star models. The fit improved dramatically, significantly better than alternatives. The helium absorption matched predictions. The emission line ratios aligned with expectations for gas heated by dark matter annihilation rather than fusion. JADESGS 140 came next. Similar properties, high redshift, compact, bright. The spectrum again showed strong helium features. Again, dark star models fit better than conventional explanations. Two objects with similar anomalous spectra constitute a pattern, suggestive. If dark stars existed at cosmic dawn, they should produce exactly these kinds of spectra. The spectroscopic analysis went deeper. Scientists measured velocity dispersions. The width of spectral lines indicates how fast gas is moving. JADES candidates showed moderately broad lines. The velocities suggested massive objects with strong gravity. This matches dark stars. A 100,000 solar mass dark star generates powerful gravitational fields. Gas in its atmosphere moves at hundreds of kilometers per second. This produces the observed line widths. Metal abundances also provided clues. The spectra showed low metallicity, very little carbon, oxygen, or nitrogen. This fits objects forming from nearly primordial gas. First-generation stars forming before significant metal enrichment. Dark stars should have low metallicity. They form from the first available gas. That gas was almost pure hydrogen and helium. JADE's candidates show exactly this chemical signature. Temperature measurements added another piece. Spectral features constrained surface temperature. JADE's candidates appeared cooler than normal massive stars. Temperatures around 20 to 30,000 degrees. Normal massive stars burn at 40 to 60,000 or hotter. Dark stars naturally run cooler. Their energy comes from distributed dark matter annihilation, not concentrated fusion cores. JADE's candidates match the predicted dark star temperature range. The evidence accumulates. High redshift, compact size, strong helium absorption, unusual emission line ratios, moderate velocity dispersions, low metallicity. cool surface temperatures. Every measurement points toward dark stars. Not every scientist accepts this interpretation. Some argue the data quality is insufficient. Others propose alternative exotic objects. The debate continues, but spectroscopic evidence grows stronger. JWST's candidates might be the smoking gun, the first directly observed dark stars, objects that existed for mere millions of years before collapsing into black holes. We see them now because their light traveled 13 billion years to reach us. Dark matter eludes us. We know it exists through gravity. Galaxies rotate too fast. Clusters hold together too tightly. The cosmic microwave background shows patterns requiring dark matter. Yet we cannot see it, cannot touch it, cannot capture it. Every attempt to directly detect dark matter particles has failed. Experiments bury detectors deep underground. They cool crystals to near absolute zero. They wait for dark matter particles to collide with atomic nuclei. Nothing. Years of operation. Zero confirmed detections. Particle accelerators also came up empty. Scientists slam protons together at enormous energies, hoping to create dark matter particles. The collisions produce exotic particles, but none match expected dark matter properties. Dark stars might break this deadlock. If dark stars exist, they prove dark matter particles can annihilate. Annihilation requires specific properties. The particles must have antiparticles. They must interact when they meet. These interactions convert mass into energy. The annihilation products carry information. When dark matter particles destroy each other, they produce standard particles, maybe photons, maybe neutrinos, maybe electrons and positrons. The spectrum depends on the dark matter particle properties. A dark star acts as a natural particle physics experiment. Dark matter concentrates inside the star. Particles annihilate continuously. The energy output depends on the annihilation cross-section. The spectrum depends on the annihilation channels. Everything about the dark star reveals dark matter particle properties. By studying dark stars, we study dark matter directly. The helium features in JWST's candidates constrain dark matter properties. The features appear at specific strengths because the dark star surface has a specific temperature. That temperature results from specific energy input. The energy input depends on dark matter annihilation rate. The annihilation rate depends on particle cross-section. Work backwards from the observed spectrum, and you extract the dark matter particle cross-section. You learn how often particles annihilate when they meet. This is fundamental physics no laboratory has measured. The dark star mass also provides constraints. A star can only grow as large as its energy source allows. If dark matter annihilation produces too little energy, the star collapses before reaching enormous size. If too much, the star might explode. Observed masses tell us how much energy dark matter annihilation releases. Temperature variations across different dark star candidates might reveal different annihilation channels. If some dark stars annihilate primarily into photons while others into neutrinos, they will have different surface temperatures. The distribution maps out branching ratios. Even the lifetime of dark stars constrains dark matter. How long a dark star shines depends on how fast it consumes dark matter through annihilation. Observations of dark star populations at different redshifts could measure this timescale. This is particle physics from astronomy, using stars as detectors, using galaxies as laboratories. The universe at cosmic dawn becomes a massive experiment studying dark matter properties. Laboratory detectors search for one dark matter particle at a time. Dark stars contain trillions upon trillions of annihilating particles. The signal is enormously amplified. What is invisible in a detector becomes blindingly bright in a star. If dark stars are confirmed, they transform dark matter research. We go from knowing almost nothing to measuring cross-sections, masses, and annihilation channels. all from studying distant stars that shone for a brief moment 13 billion years ago. When a dark star runs out of fuel, the end comes swiftly. No gradual dimming, no slow fade. One moment, the star shines. The next, it collapses. The trigger is simple. Dark matter annihilation stops. Without that energy source, nothing supports the star against gravity. The structure has no fusion core burning at the center, no radiation pressure pushing outward from deep within, just gravity. And gravity always wins when left unopposed. The collapse begins at the core, the densest region where dark matter was most concentrated. That region was also where annihilation happened fastest. When the dark matter runs out, the core loses support first. It begins falling inward. As the core collapses, it pulls the surrounding layers with it. The infalling material accelerates, faster and faster. Nothing can stop it. The star has no mechanism to halt the collapse. No last-minute fusion ignition, no bounce from neutron degeneracy pressure, just unimpeded gravitational collapse. Within hours, layers that once spanned light years compress to planetary scales. Within days, they shrink to stellar scales. The density skyrockets, temperature soars. But temperature cannot save the star. Thermal pressure is too weak. Gravity overwhelms everything. The collapse continues until something fundamental happens. The core density reaches a critical threshold. Space itself cannot support the mass concentrated there. An event horizon forms. A black hole is born. The event horizon appears small at first, perhaps just a few miles across for a 10,000 solar mass black hole. But it grows immediately. Material still falling inward crosses the horizon. The black hole swallows it. With each piece of infalling matter, the black hole gains mass. The horizon expands. This process happens catastrophically fast compared to normal stellar evolution. A dark star that shone for millions of years collapses in less than a day. The transition from star to black hole occurs in the blink of an eye on cosmic timescales. Not all the star's mass makes it into the black hole. Some outer layers might be ejected. Turbulence during collapse could fling material outward, but the vast majority falls through the event horizon. A dark star weighing 100,000 solar masses produces a black hole weighing perhaps 70 to 90,000 solar masses. Still enormous. The resulting black hole sits exactly where the dark star was. Same location in the dense microhalo, same surrounding gas clouds, same gravitational well funneling material inward. The black hole inherits the perfect feeding environment from its dark star parent. Immediately, accretion begins. Gas that was too hot to fall onto the dark star now spirals toward the black hole. The black hole's stronger gravity can capture material the star could not hold. An accretion disk forms. The disk heats up. Radiation pours out. Within millions of years, the black hole doubles its mass. Then doubles again. The rapid growth pathway begins. From dark star to supermassive black hole in a few 100 million years, fast enough to explain what Webb sees. The collapse mechanism is elegant, simple, inevitable. When dark matter runs out, the star dies. When the star dies, a black hole forms. When a black hole forms in a dense environment, it grows rapidly. The chain of events leads directly to the supermassive black holes that puzzle us. Before Webb launched, cosmologists felt confident. Decades of work had produced detailed models of galaxy formation. Simulations reproduced the modern universe beautifully. Theory matched observation. Then Webb looked at cosmic dawn. The models failed, not slightly, catastrophically. They predicted faint galaxies. Webb found bright ones. They predicted slow black hole growth. Webb found massive black holes impossibly early. They predicted gradual structure formation. Webb found complexity that should not exist. What went wrong? The models missed dark stars entirely. Every simulation assumed the first stars were fusion-powered. They assumed star formation followed the same physics we observe today. They assumed dark matter provided scaffolding, but nothing more. These assumptions seemed reasonable. We had never observed dark stars. We had no direct evidence they existed. Including them in models would have been speculation. Scientists stuck with known physics, but known physics failed to predict what Webb sees. The simulations also assumed slow gas cooling. In the early universe, gas lacked heavy elements. Without carbon and oxygen to radiate heat efficiently, cooling should take a long time. Slow cooling means slow star formation. Dark stars bypass this limitation. Dark matter annihilation heats the gas, preventing normal fusion, but it also allows much more gas to accumulate. When dark stars finally form, they are massive. Massive means bright. Another failed assumption involved black hole seeds. Models assumed seeds came from normal stellar collapse, 100 solar masses at most. Growing from 100 to 100 million takes too long. Dark stars provide the alternative. They collapse into seeds weighing thousands or hundreds of thousands of solar masses. From there, reaching supermassive status becomes straightforward. The dust problem also escaped prediction. Models assumed early star formation would produce dust like modern star formation. Blue monsters have brightness but no dust. The models could not reconcile this. Dark stars solve it instantly. They produce minimal dust because they barely undergo fusion. The brightness comes from dark matter annihilation. No stellar deaths mean no dust. Even little red dots caught models by surprise. No simulation predicted compact X-ray quiet objects at high redshift. The models lacked the physics. Dark stars explain little red dots naturally, cool surfaces from distributed heating, no accretion disk to generate X-rays, compact size from single massive objects. The failure was not stupidity, it was caution. Scientists build models from known physics. They avoid adding speculative components. Dark stars were speculative, no confirmed observations. Now Webb forces a reckoning. The known physics does not explain the data. Something is missing. That something might be dark stars. If dark stars existed at cosmic dawn, every puzzling observation makes sense. Blue monsters, massive black holes, little red dots, all natural consequences of dark matter powering stars. The pre-JWST models failed because they were incomplete. They described the universe after dark stars vanished. Webb sees the era when dark stars dominated. The models do not. We need new models. Models that include dark stars. Models that allow invisible matter to become visible light. Models that match what Webb actually sees. Astronomy and particle physics rarely intersect. Astronomers study distant galaxies. Particle physicists study subatomic particles. The scales differ by factors of 10 to the 40th power. Yet dark stars bridge this gap. A dark star is both an astronomical object spanning light years, also a particle physics laboratory where dark matter particles annihilate. Studying one informs the other. Consider what dark stars reveal about dark matter particles. The annihilation rate inside a dark star depends on the particle cross-section. Cross-section measures how likely particles are to interact when they meet. The energy output of a dark star directly reflects this cross-section. A brighter dark star means more annihilation. More annihilation means larger cross-section. By measuring dark star brightness, you measure the dark matter particle cross-section. This is information particle physicists desperately want. Laboratory experiments try to measure cross-sections by detecting rare interactions. They wait years for a single event. Dark stars provide billions of interactions per second. Temperature also constrains particle properties. Different annihilation channels produce different amounts of energy. If dark matter annihilates into photons, the energy spectrum differs from annihilation into neutrinos. The dark star surface temperature depends on which channels dominate. Multiple dark star candidates with varying temperatures map out the branching ratios. This tells you how dark matter particles decay, what products they produce, how much energy each channel releases. The mass of dark stars constrains the dark matter particle mass. Heavier particles release more energy per annihilation. More energy allows stars to grow more massive before becoming unstable. The maximum observed dark star mass sets an upper limit. Conversely, if dark stars never exceed a certain mass, the particle mass cannot be too low. Too little energy per annihilation means the star collapses before growing large. The observed mass distribution brackets the particle mass from both sides. Lifetime measurements add another constraint. How long dark stars shine depends on how much dark matter they contain and how fast they consume it. Observations of dark star populations at different redshifts reveal their lifetimes. This creates a feedback loop between cosmic observations and fundamental physics. Webb observes dark stars. Those observations constrain particle properties. Particle physicists use those constraints to design better detectors. Better detectors might directly catch dark matter particles. The connection runs deep. Dark stars may be the only way to directly probe dark matter particle physics. Laboratory detectors have failed for decades. Particle colliders found nothing. The universe itself provides the experiment we cannot build on Earth. Cosmic dawn becomes a window into particle physics. The first 400 million years was a time when dark matter particles annihilated at rates we can measure. By studying that era, we learn about the fundamental nature of matter. This is why dark stars matter beyond astronomy. They are not just exotic objects that solve puzzles. They are portals to understanding the particles that make up most of the universe's mass. If confirmed, dark stars transform our approach to dark matter research. We stop relying solely on underground detectors. We add telescopes pointed at cosmic dawn. We combine astronomy with particle physics. We use the universe as our laboratory. Confirmation requires proof. Suggestive evidence is not enough. Scientists need definitive detection. The race is on. Webb continues observing. Every deep field survey adds more candidates, more objects with unusual spectra, more compact bright sources at high redshift. Each new candidate strengthens the case or reveals problems. The telescope has years of operation ahead. Its instruments can take even deeper spectra of candidate objects. Higher resolution, better signal-to-noise, more detailed analysis. Each improvement brings clarity. One key test involves searching for specific spectral signatures unique to dark stars. Theoretical models predict precise wavelengths where absorption or emission should appear. If dark stars exist, these features must be present. Another test looks at variability. Dark stars should show brightness changes as their annihilation rates fluctuate. Normal stars vary differently. Accreting black holes show characteristic flickering. Each type has a distinct pattern. Long-term monitoring can distinguish them. Temperature measurements provide another avenue. Dark stars should be cooler than fusion-powered stars of similar luminosity, but warmer than black hole accretion disks at similar mass. The temperature sits in a specific range. X-ray observations play a crucial role. Little red dots emit almost no X-rays. This fits dark stars perfectly, but it could also fit heavily obscured black holes. Multi-wavelength observations covering radio through X-rays can break the degeneracy. Gravitational lensing offers a powerful tool. When a massive galaxy sits between us and a distant dark star candidate, the galaxy's gravity magnifies the light. This natural magnification allows much more detailed study. Computer simulations also advance. Researchers build increasingly sophisticated models of dark star formation and evolution. They predict observable properties in finer detail. Then they compare predictions to observations. The competition is international. Teams in the United States, Europe, and Asia all pursue dark star confirmation. Each group analyzes Webb data differently. Each develops independent models. Science advances through competition. Some researchers focus on individual candidates. They study the most promising objects exhaustively, every available wavelength, every possible technique. These intensive studies aim for definitive answers. Others take a statistical approach. They analyze large populations of high redshift objects. They look for patterns. Do objects cluster in specific ways? Do their properties correlate? Population studies reveal trends individual observations might miss. Both approaches are necessary. Individual studies provide detailed understanding. Population studies show how common dark stars might be. The timeline for confirmation remains uncertain. Some researchers believe convincing evidence could emerge within 2 years. Others think definitive proof requires 5 to 10 years. The universe does not yield its secrets quickly. Skeptics remain. Not everyone accepts the dark star hypothesis. Some scientists argue that conventional astrophysics can still explain observations with modifications to existing theories. The debate is healthy, but the evidence accumulates. Each new observation, each new spectrum, each comparison between prediction and reality. The dark star hypothesis survives every test so far. If dark stars are confirmed, the announcement will be historic. The discovery of a new type of star, powered by dark matter, existing only in the early universe, seeding supermassive black holes, providing direct evidence about fundamental particle physics. The race continues. Telescopes observe, scientists analyze, the answer approaches. The first 400 million years shaped everything that followed. Dark stars illuminate this critical era. Before dark stars, the universe was dark, literally. No light sources existed except the fading glow of the Big Bang. Hydrogen and helium gas drifted through space, dark matter clumped into halos, but nothing shone. Dark stars changed this. They were the first lights, not tiny flickering points. Brilliant beacons flooding their surroundings with radiation. Each dark star ionized vast bubbles of gas. These bubbles eventually overlapped. The universe transitioned from neutral to ionized. This transition, called reionization, was one of the most important events in cosmic history. Webb is designed partly to study it. But observations confused scientists. Reionization seemed to happen faster than models predicted. Dark stars provide that brightness. A single supermassive dark star can ionize as much gas as millions of normal stars. A population of dark stars could reionize the universe quickly. The timeline fits. The era also saw the first heavy elements. Normal fusion-powered stars create carbon, oxygen, nitrogen. When they die, they scatter these elements. This process, called chemical enrichment, took billions of years. But some elements appeared earlier than expected. Webb detects carbon and oxygen in very distant galaxies, too distant for multiple stellar generations. How did metals appear so fast? Dark stars might produce some metals through limited fusion in their outer layers, not as much as normal stars, but some, enough to seed early enrichment, enough to jumpstart the chemical evolution of the universe. The black holes seeded by dark stars profoundly affected galaxy formation. Supermassive black holes sit at the centers of most large galaxies. They regulate star formation through powerful outflows. They shape the properties of their host galaxies. But how did the black holes get there? The answer might be dark star collapse in the first few 100 million years. These early black holes established themselves, then grew alongside their galaxies. The correlation between black hole mass and galaxy mass might trace back to dark stars. The most massive dark stars formed in the densest dark matter halos. Those halos also had the most gas. More gas means bigger galaxies. More massive dark stars mean bigger black hole seeds. Dark stars also reveal dark matter properties during this era. Dark matter density was much higher then. The universe was smaller. Everything was compressed. Annihilation rates were maximized. After 400 million years, dark matter density dropped. The universe expanded. Halos spread out. Annihilation became too rare to power stars. Dark stars could no longer form. This makes the first 400 million years special, the only time dark stars existed, the only era when dark matter directly powered visible light, a unique window that closed forever. We study that window by looking at the most distant objects Webb can see. Every observation of a high redshift galaxy is a glimpse into the dark star era. Every spectrum is potential evidence. The first 400 million years was not slow and boring. It was dynamic, bright, complex. Dark stars blazed across the infant universe. They ionized gas. They seeded black holes. They enriched clouds with metals. They set the stage for everything that came after. Understanding this era requires understanding dark stars. Without them, we miss a crucial chapter. The hunt has just begun. Webb has shown us glimpses. Now we need the full picture. Future observations will target known candidates with increased precision, deeper exposures, higher spectral resolution, multiple viewing epochs to catch variability. Each additional observation either strengthens the case or reveals flaws. New instruments will help. Webb carries 4 instruments. Each one can study dark star candidates differently. Combining data from all provides a complete view across wavelengths. We have barely scratched this potential. Ground-based telescopes also contribute. The extremely large telescope will come online in the next few years. Its enormous mirror can follow up on Webb discoveries. Higher resolution imaging, complementary spectroscopy, X-ray observatories remain crucial. Chandra and XMM Newton continue operating. New missions are planned. Deeper X-ray observations could definitively distinguish dark stars from obscured black holes. Radio observations add another dimension. Dark stars might produce radio emission through different mechanisms than normal stars. The square kilometer array will provide unprecedented sensitivity. Gravitational wave detectors might eventually hear dark star remnants. When dark star black hole seeds merge, they produce gravitational waves. Future detectors sensitive to higher frequencies could catch these signals. Theoretical work advances in parallel. Simulations grow more sophisticated. They include dark matter annihilation. They track dark star formation and evolution. They predict observable signatures in greater detail. Theory guides observation. The connection to dark matter physics will deepen. If dark stars are confirmed, particle physicists will extract properties from astronomical data. They will design new detector experiments based on those properties. This creates a new field, astroparticle cosmology, connecting the largest structures to the smallest particles, using the early universe as a laboratory, testing fundamental physics through telescope observations. Future space missions might target cosmic dawn specifically, a telescope designed purely to study the first billion years. Optimized instruments, deeper fields than Webb, dedicated to answering questions about the earliest epochs. The ultimate goal is certainty, moving from candidate detections to confirmed discoveries, from suggestive evidence to definitive proof. This takes time, patience, careful analysis, multiple independent confirmations. But the payoff is immense. If dark stars existed, we rewrite the history of the universe. We explain mysteries that seemed unsolvable. We connect astrophysics to particle physics. We understand dark matter through direct observation. If dark stars did not exist, we still learn. We rule out a hypothesis. We constrain what can and cannot happen in the early universe. We discover what actually caused the observations. Science advances either way. The James Webb Space Telescope opened a new window. Cosmic dawn is no longer hidden. We can study the first galaxies, the first stars, the first black holes. This era determined everything that followed. Dark stars might be the key to understanding it all. Giants powered by invisible matter, shining for a brief cosmic moment before collapsing into the seeds of supermassive black holes, lighting up the infant universe. The future will tell us if they were real. The observations continue. The analysis deepens. The answer approaches. And when it comes, we will know. We will understand what happened when the universe was young, when darkness became light. That moment is coming.